We have always explored the worlds around us. With elaborate telescopes, we learn more about the stars above us. With microscopes, we are able to look inward, seeing organic worlds both fascinating and complex. With the cyclotron, we can explore even further inward, deep into the world of nuclear particles. A world so small it cannot be seen, only imagined. This imaginary world is what drew Ed Stevenson to nuclear physics.
One of the things that's always of interest to me is how people respond to the fact that I do physics. But I have difficulty sometimes explaining to them exactly what it is that I do experiments about. Because you're looking at things that are on such a small subatomic scale, it's hard for us to have any real experience of what it must be like down there where the atoms and the nuclei are. It's almost as if you're visiting a foreign country, and you've gone there to try to find out what the language is like, what the people are doing, what the customs are, what the countryside is like. Everything is new. Everything is different. You're one of the very first explorers to go there. You're seeing things for the very first time that no one has ever seen.
The world of the atom cannot be seen, but scientists have provided us with models which can help us understand. This is a well-known model of an atom. Each atom is like a miniature solar system, in which smaller particles, called electrons, orbit a central nucleus composed of protons and neutrons. Physicists study the nucleus because its structure and interactions reveal much about our physical world. We are in one of the world's foremost nuclear research facilities, the Cyclotron at Indiana University in Bloomington. Sometimes called a particle accelerator, the cyclotron is used to create controlled nuclear reactions by striking a target with a beam of nuclear particles. These scientists are setting up an experiment to find out whether a theory about the behavior of nuclear particles is true. They believe it isn't. They're one of 70 research teams chosen this year to run an experiment. Because of the intense demand for cyclotron time, they have only 4 days to complete their run.
Here are the targets, Carl. Okay. We've got the positions. Yes, it is. Okay.
Through their stories, we can learn about the process, the frustrations, and ultimately, the rewards of doing nuclear physics.
What are the signals coming in, Ed?
Well, the first thing that we've got up here is the anode from the wire chamber. And I'm going to bring that in.
Ed Stevenson is the team spokesman on this experiment. The other 3 researchers are doctoral student Carl Pitts, postdoctoral student Jim Slowinski, and Chuck Foster, coordinator of research services at the cyclotron. This experiment began a year ago when some calculations done by one of Chuck's students produced a puzzling graph.
A graduate student brought me some curves, and in view of the rainbow, I couldn't understand them. One was a large positive analyzing power, and the other...
The rainbow Chuck refers to is rainbow scattering, a theory about the way particles change their path as they spin by the target. According to this theory, the paths of the particles are bent in the same way that sunlight is bent when it passes through a raindrop or a prism. In a prism, we find a separation of light into colors: red, yellow, green, and blue. The same kind of separation occurs for nuclear particles spinning in different directions. The calculations done by Chuck's student did not agree with the rainbow scattering theory.
There's a real difference between what we expect if we believe in the rainbow and what you predict.
Think we ought to go look for it?
Ran into Ed in the hall sometime later, and we got to talking about these results. And he said, well, some time ago, you remember, I tried to point out to you that there was such a discrepancy. It's really a remarkable one. Do you know of a case or some states to look at?
Why don't I look some stuff up tonight and see if there's a good candidate? You mean something with enough cross-section and L plus a half and L minus a half close together?
That's right. I'll let you know in the morning what I find out.
We decided the best way to resolve this issue was to do an experiment.
The key to this experiment is a particle called a deuteron. A deuteron is a nucleus which consists of a single proton and a neutron. All deuterons spin, and what happens to them when they meet other nuclei is the crucial question of this experiment. To cause a nuclear reaction, the cyclotron generates a continuous stream of deuterons, the beam, which is aimed at a nucleus of an atom of tin, the target. In this simulation, the spinning deuteron bends its path as it goes by the target nucleus. What happens in this interaction was of great interest to Ed Stevenson.
The idea of this experiment is to study what's called a DP reaction. We'll bring a deuteron in on a nucleus, and it's composed of a neutron and proton that will come apart in the field of the nucleus.
In this reaction, the proton breaks off as the neutron starts to orbit the nucleus. The team believes the original spin of the deuteron, either up or down, is important in determining the path of the proton. On the other hand, the traditional theory predicts that the path of the proton will be most influenced by the spin of the neutron as it goes into orbit around the nucleus. The way to find out what happens in the reaction is to measure various angles of the proton with a detector. From the data taken at these angles, the team can determine which spin influences the reaction.
The neutron wants to be spinning.
The team members will plot their results on a graph. As data come in, they will be able to compare their results against the theory. The traditional theory predicts that for different neutron spins, there will be two curves, one positive and one negative. But if the team is right and the deuteron spin is important, the negative curve will turn positive at large scattering angles.
Something like this.
4 p.m. The beam is scheduled to be on target in 16 hours. In the remaining time, the team must finish their equipment setup and test it.
Well, I think the one thing that the experimenters seem to have in common is that they like to play around with the equipment and use equipment.
Anode coming in here, and the scintillator 1 and scintillator 2 in these first two positions.
I think a lot of them were the kind of kids that used to take things apart, and I think I've even met some who probably got everything back together and made them work again, although things I took apart didn't work after I tried to put them back together.
Actually, we may have to run that through a delay, so why don't we take it upstairs first to delay? Because
every experiment is different, and every experimental setup is a prototype. The team members must customize the equipment to fit the specific requirements of this experiment.
If we use the gate and delay generators, probably about 60 or 70 nanoseconds.
Well, this is a computer, and it controls most of the equipment in the lab. And right now we want to get the spectrometer going, so there's a number of magnets in it that bend the particles, and they have to be set to the proper currents to bend the particles the right amount, the particles we want. So I have to adjust all the magnets, and that's just done by twirling a little knob, which goes into the computer, and then the computer turns up the power supplies, which make the current go up and makes the magnet work.
S1 is on the left and S2 is on the right. Okay. So those need to go into the first two channels on the ADC.
And to set the final magnet, the main magnet, we have a system, an NMR system, that gives us this trace up here on this scope. And by centering that trace, we know that the magnet is set at exactly the right current.
So where's the trace?
I don't see it yet, Carl.
1 a.m. The setup is almost complete. Ed and Carl tracked down some last-minute problems that are typical at this stage of the experiment.
To the spectrometer, to the anode, and to the two scintillators. So we have to adjust the frequency here and also the shape. I think I want something a little bit longer for tail pulse. I think that looks about right now. Right now we're in test mode. We're about 2 hours away from having beam on target. We're trying to make sure that the electronics in the computer are really ready to go. The way that we do that is to have a pulsar generate events in our electronics as if real data was coming in. Then we look here on the screen and find out if in fact what we're getting in the computer is exactly what we expect to get.
As the team prepares for the experiment, so do the beam operators, who work in 8-hour shifts around the clock. This is Denise Pitts, wife of team member Carl Pitts. As a point of safety, each room along the beam path must be cleared and sealed. If anyone should attempt to enter these rooms later, the beam will automatically shut off. As a beam operator, Denise's job is to maintain a stable and accurate beam. The tuning process is critical. Any equipment problems here could put the experimenters behind schedule.
I think the most frustrating thing that happens at work is when you have an unstable beam. That's when something in the machine is acting up and you can't keep the amount of beam out that the experimenters want. And you know that they've gone through a lot of trouble setting up their experiment, and having the beam on target means a lot to them. It's crucial to them, and yet you can't keep it out there because some power supply has something wrong with it or some device is flaky that no one has been able to find yet.
Yes, it's especially frustrating in that since I'm working on my thesis experiment now, I tend to view beam not being ready as adding months to my sentence, so to speak. There goes early parole. And it is frustrating because you get the adrenaline gets pumping. You peak for a run, just like a swimmer peaks for a meet. And then you're sitting in there, with all the adrenaline flowing. You've got everything set up. You're finally ready to go and come close to getting results. And then the main stage crashes, or you have a vacuum leak, or something happens. And it's very frustrating. When beam is not on target, people start climbing the walls.
Friday, 4 p.m. With the run about to begin, Ed calls a scheduling meeting.
We started late on the setup, and that means we're going to have somebody here overnight. Now, that probably means it's going to be me.
Because an unstable power supply has delayed the beam tuning, the team is 8 hours behind schedule. They have only 62 hours, less than 3 days, to complete their experiment. They must be finished by 8 o'clock Monday morning, and when their time is gone, finished or not, they must turn the equipment over to the next experimental team.
Just put you on the schedule, Jim.
I'll teach you to show up.
I get everything, huh?
You get to wake up at 3 in the morning. Think you can handle that?
Nick's closes at 2. You can just walk out one door and in another.
All right, I'll manage somehow.
Carl, why don't you stay on through Monday until 8 o'clock, till the beam goes off?
Okay.
I'm going to have to cut out early and try to be ready for the Monday lunch.
The Monday lunch meetings keep the other researchers informed about current experiments.
Good.
I'll put this up and we'll look at it as we go along.
p.m. The experiment should have begun 12 hours ago.
Beam on!
Hey, great.
Well, Ed, there's your beam.
How much have you got on target, Denise?
Oh, I've got
Beam
about
operator and experimenter discuss the quality of the beam, its energy level, stability, and accuracy.
Okay, fine.
Through a remote camera, the beam is visible as a glowing spot on the scintillator, a plastic target used only for tuning.
And there it is centered.
Okay, why don't you turn the auto steering loop back on again and let's see where it goes.
Okay.
Even with the beam perfectly centered,
There it is.
only 1 in a million deuterons will have the desired reaction with the target.
Try to move the platter around about a tenth of a degree and see if we can line that up a little bit better.
Yeah, I think that would help.
Okay, well, I'll go take care of that now.
Okay.
The beam begins here, in the ion source. Powered by 500,000 volts, this machine pulls deuterons out of hydrogen atoms. At the end of their journey, these deuterons will react with the atoms in the target. But first, they must attain the tremendous speeds needed to penetrate the target's atoms. From the ion source, billions of spinning deuterons are channeled through beam lines to the first accelerator, the injector cyclotron. These large orange electromagnets guide the deuterons in a circle. Electric fields accelerate the particles, giving them a small shove on each spiral. From the injector cyclotron, the beam travels to the main cyclotron and 4 larger magnets, weighing 500 tons each. The acceleration process is repeated until the particles are traveling at nearly 1/3 the speed of light. At its full energy, the beam reaches the scattering chamber, where 100 billion deuterons strike the target each second. Only 1 in a million deuterons will come so close to the target's nuclei that there will be a reaction. This is what the experimenters are looking for. Nearby is the magnetic spectrometer, or detector, recording what happens and sending the information back to the lab computers. Because the protons are deflected at different angles, the angle of the detector is changed during the experiment to record all the reactions.
Let's go to 27 degrees. 25.7, 8, 9, 6.1, 2, 3.
The entire process, from ion source to target to lab computer, takes only a small fraction of a second.
A little more. Stop.
So what do you think, Ed?
Okay, let's check the pulsar.
8 a.m.
Okay, it looks like this
After a few minor adjustments, Ed and Carl are ready to increase the beam to its full intensity.
here, so that's good.
Doubling the beam power finally allows the data to be collected at full speed.
The peak here isn't about the right place, so it looks like that takes care of everything. So why don't we call this a run and get started?
Okay, let me go double the beam.
Okay, good.
Great.
There are a number of things that I used to do as a kid that I think really led to my becoming a physicist later on. One of them was that when I was really small, my uncle used to bring home lots of spare parts. He would do maintenance on houses and buildings, and they would come home with lots and lots of old junk that didn't work. And he'd give some of that stuff to me, and I'd sit there and play with it for hours on end, putting things together and making little pretend models of stuff. Later on, when I was older, I used to actually put things together that would work.
Suppose that thing's empty?
Yeah, that's the problem, Chuck. We've got less than an atmosphere of helium up here.
11 a.m. 3 hours after the beam is doubled, the experiment is interrupted as helium leaks from one of the instruments.
Shall I refill from down here?
Go ahead.
Okay. 1 atmosphere. Okay, we're at 2 now. That should do it, Chuck.
Okay. I'll leave this open, this closed. That gives us a reserve that's still leaking.
Right. Fine. Sounds good.
Grandmother used to send me Mechanics Illustrated. Maybe that had something to do with it. But I always knew, and it wasn't long after I knew I was going to be a physicist or a scientist in mechanical kinds of things, that I knew it was going to be nuclear physics. Maybe it was the papers at the time. I don't know. But whatever it was very definite. It was not something that I ever had to change my mind about. But it was like being in the Navy. My family had always been in the Navy, and when it came time for military service, first I was going to go, and secondly, it was going to be in the Navy. Same thing about physics. It was definite. It was decided. Why, how, or otherwise, I don't know.
Well, Chuck, most of the states make sense, but right down in here, there seems to be some stuff on the back end of this peak. Maybe we have some contaminants or something.
How does it move with angle?
Well, let's see.
The team hasn't been very lucky so far. First, an unstable beam, then a helium leak, and now it looks as if the target itself may not be pure enough. This is the most serious problem yet. If the target contains something besides tin, all the data collected so far are useless.
Could be. Is there another target made?
Bill's made one recently. Why don't I go get one?
No, why don't you go get that, and I'll keep going here.
Okay.
I make targets at the cyclotron. Targets are thin films of separated isotopes, generally. They can be compounds or just the material itself. And targets are placed at the end of the beam line, and that's where the reaction takes place.
I hear you made some 10-116 targets recently.
Yeah, for none. He hasn't used them yet, but...
You remember what thickness they are?
Somewhere around 2 and 30 milligrams per square centimeter.
Well, we'll need that 30 milligram per square centimeter target.
To provide results that are easy to interpret, the targets are made about the size of postage stamps.
I'm not surprised.
Okay. You know where it is?
Yeah, let's look in the catalog. Oh, yeah, it's in 50B. In Chuck's particular example, there was too much oxygen on the target. And that could have come from fabrication or just sitting around in a jar. Sometimes they get contaminated in the beam line itself. But I was lucky this time, and we had another target we could give him.
With the new target, the team must start their data collection from the beginning.
I'm enough of a dilettante that I really enjoy the blend of physics, chemistry, and metallurgy and magic that making thin films involves.
Like Chuck Foster, Bill Lazowski was drawn to science at an early age.
I was a boy bomb builder, and I went from there to aerospace and nuclear engineering, but I found that I just didn't like sitting at a desk all day and plugging eloquent formulas. I don't feel like I've mastered target making. If I ever do, then I'll move on to something else. I don't know that I can make the next target request that comes in the door, and that's what keeps me interested.
What's it look like?
Well, not terribly good. We've got 4 points that disagree.
But the other spin state looks fine.
Hi, guys.
Reasonable agreement.
Thank you, Ed.
8 p.m. After all the setbacks, the first crucial stage of the experiment is finally reached. Enough data have come in to plot several points on a graph.
You want to take a look at this data?
I'd rather be sure.
There's the L plus a half state. That's sort of what you'd expect.
That's nice.
The new points are checked against reference data already known about the target. This is the only way to be sure that everything is working properly and that worthless data are not being recorded.
Are we sure this is right?
Looks pretty good. As far as
The red line represents the theory. The points are the data the team has collected so far.
if you believe in the rainbow, there's not too much of a surprise.
That's right.
But Carl over here says if we've got one systematic error, we can't sort it out.
That's right. So it looks like we're going to have to go back. This point looks odd right here because it's way away from all the others. But where are we now, Chuck?
Well, we've just finished taking this point.
Okay, so you're out here at 60 degrees.
That's right.
Do we want to repeat that point or say to go back and bracket it and see if it might not be a dip instead of one bad point?
I guess I'd like to bracket that point. Take one maybe over here and one up in there just to make sure that that's a real effect there. Because if that's real, that's a dip that's not even in the calculation.
Okay, since you were nice enough not to bring us to dinner, we're going to leave you to it.
Here, have French fry. I've been eating them.
No.
Hey, what did you do?
It's your machine.
Okay, we'll see you later, Chuck.
Good night, Chuck.